quasi-two-dimensional magnets, which show some of them very spectacular properties, like, for instance, so these manganese bismuth tellurides, which are newly discovered antiferromagnetical topological insulators, where with the aid of ESR spectroscopy could provide interesting insights on the low temperature ground state and excitations and anisotropic spin dynamics, and related to the peculiarities of the non-trivial electronic structure at the surface of these materials. But there are also other compounds which are interested, which show different kinds of magnetic order. We provide some evidence so that this very well-known material, chromium chloride, is a truly isotropic Heisenberg antiferromagnet, which is quite an exceptional case. On the other hand, for instance, so this nickel phosphate, phosphosulfate, is an easy-plane antiferromagnet with strong fluctuations. And finally, so, well, this very prominent material studied quite extensively in the recent past, so chromium germanium telluride. So we provide pertinent evidence so that it's a truly two-dimensional ferromagnet with tunable anisotropy. And in my today's presentation, I will focus on this material again, so my pointer doesn't work. So now? Still not? What happened to it? No, it's not. But it worked. Therefore, it should work again. Oh, yeah, now it works. So, OK, so I will focus on this particular material in the rest of my talk. And this brings me to the outline. First, of course, I will present some information about why these materials are interested, why this emergent field of two-dimensional van der Waals magnet attracts so much attention in the recent years, and why electron spin resonance spectroscopy is a valuable tool to study magnetic properties of these kind of magnetic systems. And then I will focus on this chromium germanium telluride, which, as we argue, is a truly ferromagnetic two-dimensional material, even in the bulk limit. And so I will present you some evidence on the spin dynamics and paramagnetic and order states, and how could we very accurately characterize and quantify the magnetic anisotropy and provide evidence for intrinsic two-dimensional ferromagnetism of this material, and how this is related to the theoretical prediction which we attempted to make. And finally, so I will show so that one can control this magnetic anisotropy and tune it by applying a hydrostatic pressure. And I will end my talk with some conclusions and possible outlook. So my collaborators of this project are a team of experimentalists from EFW Dresden, around Bernd Büchner and myself. So particular valuable were contributions by my former PhD student, Julian Seisner, and a Syrian scientist in my group, Alexei Alfonsov. And so the crystals were grown by Asfartam and Sebastian Zelter. And with the pressure-dependent experiments, so we relied on our collaboration with the Kobe University, with the group of Hitoshi Ota. And on the theory side, so the group around Jeroen van den Brink in our institute was very helpful. So the emergent field of two-dimensional van der Waals magnet is not very old. So it's about, say, maybe 5 years old. So actually, many of these materials were known for already a long time. So they're magnets, some of them are ferromagnets and antiferromagnets. But then there was a renewed interest in them regarding both fundamental aspects of magnetic order in two dimensions, but also possible functionalities of these kind of materials in some advanced technologies, like, for instance, in spintronic applications. And the reason for that is that these are van der Waals materials, so that means they're easily cleavable, and one can, with not so much effort, achieve a single or few layer two-dimensional magnetic systems, which is very flexible in terms of changing its properties. For instance, depending on the chemical composition or some external stimulus, like, for instance, strain or pressure, one can change the spin Hamiltonian from truly Heisenberg isotropic spin Hamiltonian to Ising 1 or to XY1. One, in principle, can think of doping of these one-dimensional or two-dimensional layers by electrical gating. And that provides a long possible and really interesting functionalities of this system. And there were a lot of, say, very influential articles in the recent literature on that point. But actually, so the most important property of this single layer should be that it should retain a magnetic order. And this is the greatest problem, because it somehow, it confronts so the very famous Mermin-Wagner theorem, rigorously proved in the middle of the last century, that at any non-zero temperature, one or two-dimensional isotropic spin Heisenberg model can be neither ferromagnetic and nor antiferromagnetic. That means as soon as you increase the temperature above the absolute zero, so the low energy spin waves will be excited in the system, which needs an infinitesimally small energy to get excited, and the long range order will be destroyed in two-dimensional limit. And this is easily to understand, for instance, if one considers the Heisenberg Hamiltonian, where all components of the spins, interacting spins, x, y, y, z, z, are coupled by the same exchange constant. And if one calculates so the excitation energy spectrum of this kind of the system, then one can see so this, one can obtain so this dispersion relation between the energy of the excitation and the wave vector. And one sees so that for long wave excitations characterized with a very small wave vector k, so the energy needed to excite a spin wave is infinitely small. And that means so that the two-dimensional layer cannot have a long-range order, and so the spin will fluctuate from different directions in the case when the system is truly isotropic. The situation may change drastically if one introduces anisotropy. And so this anisotropy is this parameter lambda. And in this case, the energy spectrum acquires a gap which is proportional to lambda. So that means if one switches on the positive anisotropy, one can stabilize a two-dimensional ferromagnetic order in the system because one opens a gap in the excitation spectrum which is proportional to this anisotropy. If the gap is, so then one has so this full order of the spins in two dimension. If one closes this gap, the order is destroyed. So, and now, so that brings me to the electron spin resonance, because actually it turns out so that exactly this method is very sensitive to this kind of anisotropies. And if one considers so the general effective Hamiltonian, which is used in ESR spectroscopy, one can see so that the ESR response is sensitive to many kind of interactions, the crystal field, spin-orbital coupling, interaction with electron spins with nucleus spins, the Zeeman coupling, and on the right-hand side, one sees so these terms of the Heisenberg exchange and the anisotropic exchange. And very importantly is that the ESR response is in particular very sensitive to the anisotropies. So because the anisotropies, this gives rise to the finite width of the ESR signal and to a shift of the resonance position of the ESR signals in a spin system. So actually, so the principle of electron spin resonance spectroscopy is very simple. If one has a spin one half particle, so in the zero field, the two possible energy states are degenerate, spin plus one half and minus one half. One applies an external magnetic fields and one splits so these two states according to the Zeeman effect. And if one shines an electromagnetic radiation of appropriate energy, which meets so the gap between these two split states, so the electron spin system will absorb the energy and will give rise to a resonance signal. One can change the excitation frequency, and correspondingly, so the resonance field will be changed. And if one plots so the resonance field on this frequency versus magnetic field diagram, so one will obtain a straight line originated from this origin, and the slope of this line is determined by the G factor. G factor is a very important spectroscopic quantity. It's fundamental because it relates the angular momentum of a quasi-particle with its magnetic moment. So, and actually in our lab we can change so the excitation frequency by 2 orders of magnitude from 10 gigahertz to almost 1 terahertz, which corresponds to the energies of from 14 microelectron volts to almost 4 millielectron volts. And this is the irrelevant energy scale for looking for spin waves. Now, in case if the system is more complex, for instance, it has some anisotropy, so also the ESR response gets a bit more complicated. So in that case, so even in the absence of the magnetic field, some particular spin states have lower energies than the others, and this corresponds to the opening of some anisotropy gap. And the ESR responses get more complex, so instead of a single line, one in this particular case observe the two lines. And if one measures so these signals at different frequencies, one obtains two resonant branches. And if one approximates them to the zero magnetic field, one directly obtains the excitation energy in the spin system. So now, in the case of the ferromagnetic resonance, and that will be a subject of my today presentation, so in principle, in one sublattice ferromagnet, one can excite by ESR two modes. So they are degenerate at zero magnetic field, and so they have finite energy in the case of the easy axis anisotropy. So that means the magnetization or the spins, they want to prefer to stay out of the plane. And in this case, one mode, if one applies a field normal to the plane, it will develop linearly with magnetic field. The other mode will first soften, and then it also will develop linearly in a magnetic field. And this is distinct from the paramagnetic resonance, which is shown, the branch is shown here. If we have an easy plane ferromagnet, so that means the spins prefer to lie in the plane for whatever reason. So then these two modes are gapless in zero field. So they develop a Zeeman gap with increase in the field if we apply it for both directions. And this is a specific, very, very clear cut difference between the easy axis and easy plane ferromagnet. So now let's come to this particular material, so chromium germanium telluride. So as many other van der Waals systems, so they actually present a structure very typical. So this is the chromium ion, six-fold coordinated by tellur ligands, and they form a honeycomb lattice in the AB plane, and these honeycomb planes are stacked along the C direction, and they're coupled only very weakly by the van der Waals forces. And that this material is ferromagnet was known a long time ago. But recently, that was a really interesting work published in 2017 by Chen Gong and co-authors, who showed so that actually, so this ferromagnetic order present in the bulk, so this is the magnetization of the bulk material at 60, say, 5 Kelvin, something like this, is still present if one reduces the thickness of the crystal. And the evidence came from the magnetic Kerr effect. So actually, so this is the magnetization of the 5-layer, 4-layer, 3-layer, and bilayer system, which still have a robust ferromagnetic magnetization. So they couldn't measure the single layer because it was very unstable, but at least in the bitalar ribbon, so the system retains ferromagnetic order. And then there's a very important question: what stabilizes the ferromagnetic order in this material? And then insights on magnetic anisotropy were required, and so we attempted to obtain them in our measurements. So for that, so we have grown so high-quality single crystals of this material, so they're very flat and they're very chemically homogeneous, and we could confirm so that indeed, so in the magnetization measurement, they show a clear-cut transition to the ferromagnetically ordered state with a Curie temperature of 66 Kelvin, sorry. And the magnetization curves are very similar for the in-plane and out-of-plane direction, suggesting so that it's a very soft ferromagnet. So now if we measure electron spin resonance in the paramagnetic state far above the phase transition, so then we can measure them at different frequency, and the response is very isotropic. So the very sharp resonance lines, and so the slope of the frequency magnetic field dependence gives us the G factor value, and it's almost very close to the spin-only value, which is expected for the chromium 3+ ions because they don't have an orbital momentum in the ground state. So, however, there was a first surprise that as soon as we lower the temperature below 120 Kelvin, so this response gets progressively anisotropic. So the resonant field for the out-of-plane direction, so it goes one way, and the resonant field for the in-plane direction, it goes the other way. So actually, so this is a signature of the development of the spin-spin correlations, low energy, low frequency spin-spin correlations, which generate quasi-static local fields on the ESR time scale. But importantly, so these shifts, they are present or start to develop at temperatures which is twice as large as the ordering temperature. This is very unusual for a conventional three-dimensional magnet, where as soon as the correlations start to develop in all three dimensions, the magnetic order sets in. And that was the first indication that even in the bulk crystal, so we're studying a bulk crystal, so we see short-range two-dimensional correlations at temperatures far above the ordering temperature. So the next evidence, though, that this material is truly intrinsically low-dimensional, even in the bulk limit, is the angular dependence of the ESR line width. So the ESR line width is given by the anisotropic dipole-dipole interactions. And therefore, the width is determined, is somehow affected by the relative direction of the applied magnetic field and some symmetry axis of the interacting spin system. And in the paramagnetic limit, actually, so the ESR response is ESR response is given by the spin correlation function, self-correlation function. So it's time dependence. And usually in the paramagnetic limit of a three-dimensional system, so the spin correlation function is decayed very rapidly on the time scale of the isotropic exchange interaction. But in the two dimensions, there is a long tail of so-called diffusive tail of the spin-spin correlation where the long wave correlations, so they survive at times much longer than this characteristic scale of the isotropic exchange interaction. And in the limit of the short time scale, so all kind of dipole-dipole interactions, they contribute to the line width, so they call secular and non-secular terms, and they give rise to a very specific cosine square plus 1 angular dependence we indeed observe at room temperature. However, in the 2D limit, so where this diffusive tail is prominent, so only one part, the so-called secular part of the dipole-dipole interaction is present and survives, and it has a very distinct angular dependence. This is 3 cosine square minus 1. So one has no more a minimum and maximum in these extreme directions of the fields, but it has a minimum of the so-called magic angle of 54 Kelvin. And so this was the second evidence that chromium-germanium telluride is intrinsic two-dimensional ferromagnet in the bulk limit. So now if we enter the magnetically ordered state, indeed what we observe, so that the paramagnetic mode is now split in two ferromagnetic modes, suggesting that indeed so we're dealing with the easy axis ferromagnet. So now you can see so that one of the branches, it has a finite offset here, and the other one is softness as a certain critical field. And if one measures the angular dependence, one clearly observes so that at different frequencies, so there is a clear-cut angular dependence. Here one has to mention a difference between the electrospin resonance and ferromagnetic resonance. In electrospin resonance, so one measures the response of the individual precessing spins. So they could be coupled by exchange interaction, but nevertheless, there is a response of the individual spins. In a ferromagnetic resonance, this is a response of the total magnetization of the sample. So the magnetization precesses around the applied magnetic field, and one can change these oscillations by applying a microwave radiation of an appropriate frequency. And we could model so this development of these ferromagnetic resonance modes by calculating the oscillations of this magnetization vector, which are given by the angular derivatives of the free energy. And the free energy is composed of 3 terms. So this is the Zeeman energy, the intrinsic magnetic crystalline anisotropy, and also the so-called shape factor, which due to the specific shape of the signals, of plate-like shape. And so we could, from this, we can accurately calculate the magnetic anisotropy energy, which corresponds to about 83 microelectrons per formula unit, and the sign is positive, so that means it's definitely easy access which is required for the stabilization of magnetic order in the single layer limit. So how reasonable is this number? So that the theory helped us in this context. So our theory collects, performs some density functional calculations using all electron full potential local orbital code, generalized gradient approximation, and also what was important to add the correlation energy U. One important findings in this computational study was the band structure. It turns out so that the conduction band, in this case, so it's gapped because it's a semiconductor, but it is fully polarized at low energies. one has so here almost full minority spin polarization. It suggests that if, for instance, one single layer could be gated and doped by electrons, so this will generate a fully polarized electron gas, which is very useful for potential functionality of this material. Next finding was that actually it was really very necessary to add the correlation energy between the electrons, because in its absence, so the calculated magnetic anisotropy was of the easy plane, which contradicted the experiment. However, increasing U up to, say, 2 electron volts, and quite a good number, so one could really find a very good match between experimental findings and the theory, suggesting so that actually, we have a reasonable description of a single layer system in terms of the single ion anisotropy and polarization of the electron bands. So now the final question, which was interested to us, how can we change this magnetic anisotropy? Because it would be important to have some handle which could enable us to tune these very important magnetic properties. One possibility would be to apply pressure, hydrostatic pressure. In that case, so we thought we could see that by changing the properties of the ferromagnetic resonance. In the absence of pressure, so we have these two excitation modes, which have different energies due to the magnetic anisotropy. If, for instance, we increase the pressure, it might happen so that the anisotropy gets smaller, and therefore these modes would merge into a single line, and eventually, so we possibly could even turn the type of the magnetic anisotropy from easy axis to the easy plane. And indeed, it was realized in our experiment. And this is, for instance, so a ferromagnetic resonance line at a given frequency at ambient pressure. Now we apply pressure, and you see so that the line continuously shifts to higher fields. So there is a distinct effect, a very appreciable effect of pressure. So if we measure that at different frequencies, what we see is that this branch, so indeed, so with increasing pressure, it continuously comes to the isotropic limit, and we will see, so these are two distinct branches at zero pressure, and they merge into a single isotropic resonance response by increasing the pressure. So in fact, so it turns out so that we can close, with pressure, we can close the magnum gap. So we get an isotropic limit. Of course, that was a question, so what is the reason for that? It might be so that with the pressure, we simply suppress ferromagnetic order, or that reduce the magnetization. For that, so we made the static magnetization measurements under pressure, and we found that up to the critical pressure for the closing of the gap of 2.4 gigapascal, so still the ferromagnetic order is present in the bulk limit, and the magnetization doesn't change substantially. So that means we reach the isotropic limit by changing the intrinsic magnetic crystalline anisotropy so that it's fully compensated now by this shape anisotropy, which is always in plane. So, and now, of course, so that is, it again doesn't work. No? Yes. So that means, so we have a handle. So in the absence of the applied pressure, so we have a gap, and we have potentially in one dimension, in the single layer limit, still a ferromagnetic order. But as soon as we apply pressure, we close the gap, and the order is destroyed. And so we can think of some potentially interesting conceptual device when we put, say, this layer of chromium germanium telluride on a piezo substrate, and if the substrate is unstrained, so then we would have the time-independent out-of-plane of magnetization of the single layer. As soon as we apply a voltage to the substrate, we contract the layer, and so the magnetization is lost. We can apply a new pulse, and it goes like this. And so this is an interesting potential functionality. We can integrate so this kind of B layer into some spintronic device, for instance, to generate spin-dependent currents, manipulate the spin-dependent currents. So that brings it to the conclusions, so that we can show that actually this material, bulk crystals of this material still show the properties of intrinsic two-dimensional ferromagnet, which has an easy access magnetic anisotropy, and we can accurately quantify its value and show that it's required out of plane, so easy access anisotropy in good agreement between experiment and theory, which also predicts so that if doped, so that we could have almost fully spin polarized two-dimensional electron gas. And also, very importantly, we could find a way how to tune the anisotropy in this material by pressure, and we can propose that we could have in some strain control of magnetic ordering heterostructure. So thank you very much for your kind attention.
Is it possible to say something about exponent and how far it's from really a transition from anisotropic two-dimensional anisotropic ferromagnet to isotropic ferromagnet?
In terms of critical exponents, actually, so the critical exponents, so that that would imply measurements. In the case of ESR spectroscopy, of course, this critical exponent should manifest, for instance, in the broadening of the ESR line. So because the ESR line is a measure of the correlations. But unfortunately, so in these particular experiments, we couldn't do that. So because of the technical complications. So as soon as we apply pressure in the pressure cell, so we have some unwanted distortions of the ESR line. Therefore, we could reliably determine the resonant field. That's not a question. But the line shape is distorted. And therefore, so the determination of the width is getting problematic. So we didn't attempt to do that.
Thank you for the nice talk. A question about this intrinsic two-dimensional ferromagnetism in this material, bulk. When you say this, do you mean that each individual chromium layer behaves in such a way as if the adjacent layer did not exist?
Almost.
Almost. Because,
because it does exist eventually, because otherwise you wouldn't have an, I don't, so otherwise I would say so that you wouldn't have such high Curie temperature as it is.
And then it drops when you go thinner.
Yeah, because it reduces. So this work shows that, not our, but this work on the few layer system, so they show that it's reduced.
But it's reduced due to the, let's say, reduced dimensionality, or because the anisotropy weakens as well?
This is not clear. So possibly these are both effects.
Is it possible to measure flakes with your technique?
Not in this pressure experiment. So unfortunately, so because this pressure, the pressure cell reduces the sensitivity by orders of magnitude. Because so you have a tiny sample in the very big pressure cell, which you have to expose to the radiation. So the density of the microwave radiation is really very small at the sample.
I see. So will be interesting anyway to do so somehow.
So we will try to. We are going to try that in the strain samples, not the hydrostatic pressure conditions, but on the strain conditions. So this is what we plan to do. Of course, well, we are not only ones who are interested in this material. Well, you see, so there's, of course, a complementary study. First insights into the presence of anisotropy, they came from the static magnetization measure. But as you have shown you, so these magnetization curves are very similar for the in-plane and out-of-plane direction because it's a soft ferromagnet. And therefore, really to quantify the anisotropy, you have to look at the spin waves. An alternative approach, of course, that would be, for instance, the inelastic neutron scattering, which so far I don't think that it was, the elastic scattering was made on this system, but inelastic was not. But the problem of the inelastic neutron scattering, it's a very good method, so there's no question. But it has some problems with the energy resolution for small q vectors, because the intensity of the signal goes down, and so there is some instrumental resolution issues, and therefore, if one wants to look for long wave spin excitation, so that the ESR, which doesn't have problem with it, so is a more sensitive and more precise method.
Thank you very much. think we needed to end this interesting report, and Vladislav, this.
Oh, yes, so that's my pleasure. Thank you very much.
Yes. And next, our report, Dmitry Efremov, EFW, Institute Dresden.
Oh, yes. Wait a moment.
Okay, thank you very much, and I would like to thank the organizer for inviting me to present our current work. And basically, this work done mostly by my postdoc and diploma students, Alexey and Artem Nasenko, and we just trying to get what are the low energy metastable state in these dichalcogenides, which is basically also van der Waals materials. So basically van der Waals materials and this region started to be very interesting because of the graphene, that we can mechanically make various structures, and by either mechanically or chemically, and we can control basically this structure. There are a lot of different materials. I would just say what I want to present. First of all, of course, very close to what we have in graphene are dichalcogenides. Here we have very similar structure, similar, okay, boron nitride. So here, for instance, boron nitride, we have boron and nitride, which are forming hexagonal structure. The same type we have in dichalcogenides, that this is a very two-dimensional material, and you can quite easily to split. There are two, okay, this is the main families which we investigate in van der Waals. As I told that dichalcogenides, also phosphorine and other materials, and okay, was presented again. This is not dichalcogenides, but this is more complicated structure, which was presented by previous speaker. So I will, and if you consider all these materials, in principle, we can have two types. We can have insulator, like here. This is this magnetic insulator, but also we can have different type of the semi-metals. And in particular, the richest life is in dichalcogenides, because there are a lot of different dichalcogenides, and some of them are basically like here. We see a very big gap semiconductors, but some of them from this group can be also semi-metals. So, and there are two types of main type. Okay, good. And dichalcogenides basically dichalcogenides basically we define that we have transition metals. Usually we are considered 3D transition metals, and also two halogen atoms, which are basically sulfur, selenium, and tellur. And there are also dichalcogenides which is also with 5D elements, but basically I will speak only on one very small family on titanium. So the characteristic feature of dichalcogenides, there are two different structures, and therefore it's very important, and the same compounds can be in two different structures. This is in trigonal, with trigonal symmetry, which is presented here, and basically one means that it repeats itself in one layer, and in two layers, this is 2H structure, which is hexagonal, has hexagonal symmetry. And usually okay, most of the structures, if we can see, this is the present what we know, and basically these materials were investigated a lot in the 70s, and we know about a lot about these properties of this material. Nevertheless, we find new and new experiments. And basically, if you can see that from this table that most of these materials can be presented in both form, hexagonal and trigonal. And here, star means that they can be metallic type, or this is 2-star in the semiconductors type. So, and I will speak about this series, which is basically presented as a trigonal symmetry semi-metal type. The most interesting here is titanium diselenide, basically because, first of all, of course, if you look to the structure, it's a layered material like we know cuprates and iron arsenide. Therefore, first it was investigated as a material where we have superconductivity. And superconductivity material very similar what we have basically in cuprates or iron-based superconductors. That was 2011. Basically, already after 30 years of knowing these compounds, people decided to intercalate these materials and to see what happens. So, what is similarity in all these cuprates? The parent and iron-based superconductors, the parent compounds are magnetic. And then if we dope or apply pressure, basically this magnetism goes away and we have room for superconductivity. And exactly the same we have for charge density wave, which appears in titanium diselenide. If we apply, if we intercalate by copper, charge density wave goes away and we have superconductivity. Therefore, it was interesting just to investigate what is the reason of superconductivity and what kind of superconductivity we have in this case. Because it's very similar what we have in high temperature superconductors. So, for me, right now, the most interesting, this is the same as in cuprates, the normal state properties. So basically, it's even much more mysterious than this charge density wave than superconductivity itself, at least from the first point of view. So how do we see that charge density wave? Basically, if we consider pristine compound and consider superconductivity, temperature dependence, that then it goes more or less as semiconductors type up to some have a peak, and this peak corresponds to charge density wave transition. That was the first how people found this. Charge density wave is the following structure. In principle, this is a structural transition, what we see in X-ray. That here we have the structure where I have only titanium atoms, two-dimensional titanium atoms. And the transition or charge density wave is basically we see like a shift of the free atoms around one central towards this central atom. And we have basically this structure. And also because we have restructuring, we see the same in ARPES, and ARPES basically at high temperature, and we see two pockets close to the Fermi surface. One at gamma point, hole-like pocket, and electron-like pocket around M point. And if below this transition we have restructuring, first of all we see the opening the gap at gamma point, and also we have the we see the folding of this gap which coming from the endpoint. This is very, very small. So this is the evidence that we have really charge density wave. And also the second experiment, also quite interesting, was done with STM, measuring what kind of the charge density wave happens near to the surface. So this group say that the following, that in principle STM is sensitive not only to the very last layer, but also the next one and after the next one. And they found 3 different domains, and in each domain they see charge density wave which happens in one of the direction. Altogether, this is triple Q charge density wave. Just for description of this charge density wave, we need simultaneously 3 vectors which is 120 degrees to each other. So, and recently there was additional experiment, which in point contact experiment in our institute. Point contact spectroscopy is the following. Basically, we take a very thin tip just to the surface and measuring resistance in this case. Usually, okay, I just showed the usual picture, what was expected and why people are interested in this. One can get information of electron boson coupling in this case as the second derivative of the voltage over the current. So, and this value, the second derivative, is directly, one can show that in this case it's directly proportional to the electron phonon coupling alpha quadrat f. And basically that was the main motivation for this investigation, just to see how strong is electron phonon coupling. So, and this is typical what was done, for instance, for iron-based superconductors with copper point contact, and we see that the strongest is at 20 millielectron volt, and if you look the bosons there, basically one can see that it's basically corresponds to bosonic type, namely with this peak, and that was the reason. But in addition, what was found is quite interesting, that if we are starting here, and this is resistance, the first derivative of the voltage over I. And what was interesting, that if we apply this voltage, it's a metallic state. It's quite small resistance. The resistance is of this point contact is about 10 ohm, and it's different. It depends how you prepare this contact, and every time you can. This is a little bit uncontrollable process, but nevertheless, if you are doing statistic over 100 different point contacts, you can get the following. So if you apply the voltage, basically it's reversible. If you increase with applying the voltage, you have increasing of the resistivity. There are several reasons of the increasing of resistivity. As I told, the first, this is because increasing of the response of the electron phonon coupling, backscattering at the point contact. The second, because of the thermal effect. But nevertheless, if the voltage is quite small, below some threshold, we always have the same properties and go along the same line. But if we increase above, and in this case about 1 volt, then we are going to completely different curve. And this is semiconductor type of this curve. So basically, and we will stay forever at this basically semiconductor state. Something like, okay, I'm saying something like semiconductor, but definitely this is exactly what people see in semiconductors, this type of the behavior of resistance versus the voltage. And what is interesting, applying to the opposite direction, we're switching back to this low resistance state and can stay here. So this is like a switchable effect, which appear because of the response to the current. So, and what is interesting, that it survives up to the room temperature. Of course, it becomes less pronounced. Here you see this is 2.5 Kelvin, and at very low, this is the black curve, and the blue one is at room temperature. And the threshold becomes smaller and smaller. Similar effect was observed also in some Wall-semi metals like tungsten telluride and molybdenum telluride, which are basically also van der Waals materials, late materials. So, and this is one of the reasons of our investigation, just to see if we have some low energy metastable state, to which we can switch our material by the current or electric field. The second, also, we were quite curious why, in the case of titanium diselenide, we have charge density wave, which basically goes away with the pressure. But if you look titanium ditelluride, which is basically isovalent, we have no charge density wave. If you look just a simple picture, band structure calculation, GGA, we see that there is no so big difference between all this material, titanium from band structure, electronic band structure to point of view, titanium sulfur, titanium diselenide, titanium ditelluride. Basically, this is free covers. So in all these cases, we have around gamma point, we have hole-like pockets and electron-like pockets around L point. So basically, in all these materials, we have so-called nesting when we have similar by the volume electron and hole-like and electron-like pockets, which are shifted by some vector q. And this is for very long time was considered like the main idea behind of this material. Basically, there are several theories which try to explain what is the origin of charge density wave. One is just phonon condensation. This is just a normal structural transition, because in the structural transition, what we have some structure at low temperature, then increasing temperature give you motion of the molecules. Therefore, because of this entropy, another structure may be more preferable. So, but most of the theory are coming from electronic mechanism. This is either excitonic band. They are very similar and very similar by idea that we win some energy because opening the gap. So excitonic band Young-Taylor instability, also orbital order or interpol, more complicated mechanism for this charge density wave. And basically the idea is the following: if you have some whole band around gamma point, electron band around L point, then we can win energy if they open this gap in both cases. And basically, this is because we have nesting between this point, and energy of the quasi-particle is equals minus energy, so electron hole, and then we have airplane instability, divergence of susceptibility, and so on, and we have either spin density or charge density wave depending on the interaction. So, what we did, we decided to look, first of all, if we can consider of all energy structures. So basically, we are saying the following, that let us take several atoms and predict what kind of the structure can exist in this case. And considering not only the ground state, but the lowest metastable states. So we are saying that let us put in some volume 5 atoms, 3 of them titanium, 2 of them selenium, and just look what will be the energy. This is, we use so-called evolutionary algorithm. It means that we are putting the first structure and calculating the energy. After that, making a different movement, shifting of the a little bit atoms by some algorithm, flipping, and so on. And basically, what we are doing, we are considering some multidimensional space of the energy. So basically, depending on the distance of the titanium and selenide. So basically, of course, it can be mountains. It can be basically some low energy states, and we are looking and trying to find. And we have many different, can have many different local minima, like here, and then we want to calculate all the local minima. It means that in principle, the system can exist in this local minima as long, very long time, until it can go to the ground state, at least at low temperature. And if we consider everything, we can consider if it's possible to have semiconductor state with low energy, and if we can have the transition. So basically, the idea is I told that we have some ratio of titanium and selenium, and then calculating with this number of the atoms all the possible structure, and after that relaxing all these structures. So, and also we calculated some triple states like selenium, titanium, and sulfur, and tellur. Okay, but I will speak about basically titanium diselenide and titanium ditelluride. Okay, there are some technical issues with all the dichalcogenides and basically all the material van der Waals materials, because of the large distance and because of the van der Waals forces, that you need some correction for these van der Waals forces in the calculation what we use, and basically this is the result. So this is the result for titanium diselenide and titanium ditelluride. What we see? So in principle, at high temperature, the ground state has the symmetry, the space symmetry 164. This is the zero energy. This is what we name disordered state. So, and the state, with charge density wave, it's not even present here because it's higher by energy. So, and we see that in the case titanium diselenide, we have a lot of different minima with this type of symmetry, and this is lattice constant. And basically, all they are even smaller by energy than this is trigonal 1T structure, and they are lower a lot of, and basically they can be explained in the terms of different type of charge density wave. That was the main point, and investigate if you have semiconductor state. So, in the case of titanium ditelluride, we see that the lowest state is this 164. This is exactly disordered state, and no low energy metastable state. Basically, already what I want to say that already on the level of the Coulomb interaction, the material have the preference towards of the charge density or spin density wave. And by this calculation, we can say that if it will be there is instability towards charge density wave. This is distortion which can be presented in this case how to present the structure. So this is can be single Q, double Q structure, and triple Q structures. So basically, we haven't found any good basically semiconductor state. The best one is presented here, but nevertheless we didn't find. It means the mechanism probably is not just transition to another, but this also vacancies and interstitial atoms are very important. So we saw, okay, let me skip this as quite, so we saw, okay, sorry. We saw basically that yes, there are some states with quite low density of states, but this is not in reality a gap or very small gap. And also, okay, this is, and this basically also can be explained because of the all this state which is moving of the atoms can be explained by various vector of the nesting between these pockets. And if we find, so basically we find everything in coordinate space and in the momentum space, we could find corresponding interaction between different pockets. And okay, let me skip and come to the conclusion. Basically, what we found that basically the already on the level of DFT, the materials with okay, very similar materials, isovalent materials, with already on the level of DFT, we see that they are very different. So some of them basically can have metastable state, some of them do not have a metastable state. And this probably, if we include multi-particle physics, it will give us a true triple Q state, which we see in the experiment. That's all what I wanted to say. Thanks.
Thank you very much. And your question, please. I have a question. You told about theoretical prediction, some stable, stable structures for this compound, and exists some experimental with experiment, this prediction and experiment. This is
so in principle, not for titanium deselenide, it was quite much investigated. I know that there are several compounds which already were using this technique. First was predicted, and after that found in the experiment, especially at high pressure. This is nitrides or iron nitrides and some other nitrides, which first were predicted and after that found the experiment. This is a new technique which is just growing because of the computer time it needs a lot.
Thank you.
So do you observe some clear trend on the role of the spin-orbit coupling for the charge density wave instability? For instance, if you go from sulfur to selenium and tellurium based systems, does it play any role?
No, we do not see any role.
That is surprising.
it's surprising. So basically, if I compare titanium sulfur and titanium diselenide, there's almost no difference. I have, for both of them, a lot of metastable states. There are already a big difference between sulfur and selenium, but we do not see. So this is something which is okay. This is something because of the small, very small pockets in titanium diselenide and much larger pockets in titanium ditoluride. So here, the closest to the Lifshitz transition, when they disappear, it's very important. Where is the optimal? Unfortunately, right now we cannot say. This is still investigation because we have only 3 materials which we can compare. That was our first question about orbital, but we can calculate this as with orbit, without orbit. Okay, there is a little bit difference, but titanium ditoluride is very different from titanium diselenide.
Okay, if question is absent, now thanks Peter again. And your certificate.
Oh, thank you. Great pleasure.
Yes. And the next speaker, Joseph Betoros from Loughborough University. Mhm. Thanks.
Thanks. Okay, so thank you very much for giving me the opportunity to present the work of a number of years, actually, recent years here. And what I'm going to present is introduction of Fermi surface topological transitions and therefore Van Hoff singularities and higher order Van Hoff singularities, which is the consequence of them. I will spend a little bit of time to give you the basics of the classification of this type of singularities. Although these are not van der Waals materials, I will talk about the 2 ruthenate sodium 3 ruthenium 2 oxygen 7 and the superconducting 1214 because these theories have been tested to these materials. And then I will move, because I was asked to present possibilities about van der Waals materials, so I will try to convince you that whatever I present in the first parts is of high relevance to van der Waals materials. So why are Fermi surface topological transitions important and the associated Van Hoff singularities is because we have, in the case of the usual, the ordinary Van Hoff that I will explain mathematically if you like what it is, a logarithmic power law divergence in the density of states in 2 dimensions. And if you go to higher order Van Hoff singularities, things become more dramatic because we have power law divergence in the density of states. Because of that, we have slow fermions, so interactions effect becomes very important, and all these are susceptible to new phases. if we have one of the two classical type of Fermi surface topological transitions described by Lipschitz. One is the neck formation collapsing, which is the usual, the ordinary Van Hove. The other is the new pocket appearing or disappearing. And in this case, also, it has been shown that there are surprisingly new effects because even through a new pocket that appears or disappears. So a bit about the classification of singularities. The gradient of the dispersion relation has to be 0 in any case in order to see something very interesting in the density of states, diverging if you like. And then depends on what happens to the Hessian. In the 2D, it's a 2x2 system where that you take into account that the Hessian is the second order derivatives in certain order. We form the determinant of that. And if it's negative, then we have the ordinary critical point, the ordinary Van Hove singularities that leads to logarithmic divergence in the density of states. And it is of the type kx squared minus ky squared that we know. If this determinant is 0, then we have higher order Van Hove singularity. So the density of states diverges with an exponent if we set the Fermi energy at 0. So this gamma is negative. And what we found is that both the exponent but also the ratio of the coefficients above, below 0 are the D's that I've got there are universal and are preserved under smooth coordinate transformations. So this is not important, but it's important to convey the message that how we do things. We distinguish between state variables, which in our case in the two-dimensional systems, kx, ky, and then control parameters, which is the hopping strength, chemical potential, magnetic field, etc. With the usual 2 state variables in 2D and the maximum of 7 control parameters, then we have 17 types of catastrophes in 2D, no more, no less. This is exactly the number of different singularities that we can have, and each one is unique higher order singularity. We have a general polynomial expression for the energy of the system, if you like, and this is, in that language, universal unfolding. We can forget about that, but here it is an important part that we can classify uniquely by 4 integers. Winding number, I'll start with the last one. Winding number is if we go around how many times we change the sign of the dispersion relation. So when we have holes or electrons, if we go around the point. Corank is the number of 0 eigenvalues of the Hessian that we mentioned before. Determinancy is the order of lowest order Taylor expansion that describes this singularity. And codimension is how many monomials are missing. So basically, the lower this is, the easier it is to get to a higher order Van Hove singularity, because we have to forget about low number of monomials. So just for fun, if you want, you see by eye that these 2 may be almost the same, and this and that almost, very different. What are these? In kx, ky are the energy contours, and at 0 we have a critical point. But what happens if you do exactly there is a prescription how to find all these indices, all these integers. The first one has C1424, and this is exactly the same as the C1, 1424. So basically, it will give us the same exponent gamma equals -14, and this is cusp. This one and that one correspond to a cusp singularity, while the one in the middle, which looks similar to this one, has different integers and corresponds to a different density of states divergence with -1/3, and it's classified as butterfly. Now, what we had done more is to consider symmetries and take into account the different Brillouin zones. So there is a complete classification based on reflection symmetry, the rotational symmetry, combined with translations on different lattices. And we took all the 17 wallpaper groups into D, and we classify the possible singularities along the at the high symmetry points of the Brillouin zone. Sorry. Good. Now let's move to real materials where these have been applied. One is the 327 sodium ruthenate. This has been known for many years, and because of its purity and good Fermi liquid physics, it was thought to be an example and a paradigm of quantum materials to be understood. Nevertheless, I will show you briefly big questions that were posed for many years and they were unexplained. It's a bilayer material. The conduction is in ruthenium-oxygen planes. Early, it was discovered to be a metamagnet, especially if we focus on magnetic field along the C-axis. This is around 8 Tesla is the metamagnetism, but it's not a simple metamagnet. If you rotate slightly along, if you deviate from the C-axis, the magnetic field, there is a strong anisotropy in resistivity along A and B direction. And this people think that it is a nematicity is a new order that plays a role, etc. Moreover, I mean, this notion of nematicity was more or less destroyed when in 2014 there was an SDW observation in that phase. And you see that if the theta angle, so basically it's along, magnetic fields along C-axis, we have 4 spots, so 2 equivalent directions, no difference in the resistivity along A and B. If you tilt a little bit, then 2 of the spots go away, and there is a big difference in resistivity. So the conclusion is that you have an SDW, and then with the magnetic field you can align the domains, and this is the anisotropy that you could see, and not direct related to nematicity, which cannot show any SDW. Moreover, the more intriguing findings were a bit earlier, that in that ordered state where we have the SDW, where at the borders we have the metamagnetism, entropy is higher. Completely counterintuitive, because you expect in an ordered phase entropy to go down because you gap parts of the Fermi surface. Moreover, in thermodynamic measurements, these red lines were of specific heat divided by temperature in a magnetic field were 1 over H minus. So these red lines follow 1 over H minus HC left and right. All these were puzzles. You don't expect in a good Fermi liquid this behavior unless something fundamentally different is there. And the phase diagram is that we have two different kinds of SDW, the A phase and the B phase, with slightly different Q vectors in the A and B phase, but the difference is small, and this is measured along these hatched lines. Okay. You do get this if you have singular density of states. If you have a power law divergence, which can give us this 1 over H, for example, and also the inside is that if you have divergence in the density of states, yes, then you may expect that the entropy here is higher than outside because you have so many density of states, and some of them are gapped because of the SDW, but you are left with so many different, so that you can have the entropy increased inside the ordered phase. I was discussing this with Dima, and Dima was willing to use the capabilities with DFT calculations. Instead of the magnetic field, what we could do is to mimic the effect of the magnetic field with a magnetization inside, per unit cell. And then if we focus at the X point, so basically at the corner of the Brillouin zone, you see magnetization 0, nothing happens. 0.2, nothing happens. 0.4, 4 pockets appear. And 0.5, they merge here into a topological transition. And then a little bit above, you see that then this is destroyed, this topological transition. What this means is basically that we can have we know that these so-called small gamma bands are the ones who respond to magnetic field, and the rest are not so sensitive to the magnetic field. We can do a simple thing, and we can write down an effective dispersion relation, a k squared plus something k to the 4 cosine for phi. This exactly mimics what I showed you before. Mu in this case, if you tune this to 0, is the distance from exactly this Fermi surface topological transition that gives a higher order one-Hopf singularity. If you do it carefully, then the density of states as a function of the distance is proportional to an elliptic integral. We have natural energy scale a squared divided by 4b. And if we are at a distance away from the critical, which mu c 0 in our case, then effectively we see this dispersion relation with exactly the exponent that we like, and which translated will give us 1 over h minus hc dependence in the specific heat. There is a jump at mu equals 0 because of this part, and 4 Van Hove saddles coming together. So schematically, what we have is 4 Van Hove saddles coming together and 1 electron hole pocket forming in the middle, and it's equivalent to 4th order saddle. So this is exactly what we expect. And if you write down Cartesian coordinates close to the singularity, this is what we've got. And from the singularity theory, it's classified as the name is symmetry restricted parabolic singularity X9. And this K, as long as it's less than -2, which in this case is close to -6, then we have exactly, we stay with this singularity, and we have 2 control parameters in the system. So this observation led to the partial solution of the puzzle of 327, because we can literally explain the specific heat. We can explain the increase in entropy inside the phase. And we can explain by various methods why we see, also C over T going as log T at intermediate temperatures. And there is question mark whether we can explain also the SDW value Q. What we got for free is that these 2 parts are almost Q, but what complicates the situation is that other parts of the Fermi surface are also at a distance almost Q. And since we are playing with very tiny differences, we are not sure what contributes to SDW. If we are taking parts that were there before the singularity, then it led us to a very interesting question. What is the fate of SDW when a higher order Van Hove singularity appears? So think about 2 nested parts of the Fermi surface. Bring, because you change magnetic field, something, a singularity at some point, and then ask the question, what will happen to the singularity? Naively thinking, we would expect that you are going to kill this singularity. But what we surprisingly found that anything is possible in multi-orbital systems. Even the enhancement of the critical temperature of SDW by order of magnitudes, by orders of magnitude. And this is in a paper here. I mean, if you would like, we can discuss separately details of that and what conditions you may observe that. Does quantum criticality play a role? Yes, T log T is a signature of quantum criticality. We have from A to B the SDW phase that we haven't explained, and all the scaling at SDW transition can affect the details within the phase. Good. Second, so extended Van Hove singularity in Schrodium in 214. This is a different Schrodium ruthenate. It's a bit more famous because of the superconducting properties. It was the first non-cuprate layered superconductor observed. And in 1996, you see a paper by, one of the co-authors, Betnord, who talk about Fermi surface and extended Van Hove singularity in this non-cuprate superconductor. And exactly same time, extended Van Hove singularity non-cuprate layer superconductor by a different group. Good. We thought that now the notion of extended there is a bit vague. Now we have the tools to analyze this. This is extract from a 96 paper. You see what extended means, that you have almost flat or with higher order saddle. This is energy as a function of k, kx or ky in two different directions around m point. And if you go from gamma to x, then you have three crosses. People now, especially groups in St. Andrews, did two different classes of experiment. Quasi-particle interference experiment and ARPES measurement, and understood that what is extended is a surface state of 214 due to rotating of octahedra of ruthenium oxygen 6 octahedra close to the surface. It is energetically favorable, this octahedra, to rotate different from the bulk, so you can observe this type of singularities. Now, a small digression, because we wanted to use the input from both experiments to give a final answer, but polynomial fits along Brillouin zone cuts may not help due to various reasons. Might not be enough to diagnose a higher order of singularity, and also what you ideally would like is to start tuning this, and we cannot, this does not help us to track the effect of tuning parameters. So in recent work, we applied an extension of Feynman-Hellman theorem for multi-band system to get the right tools to be able to analyze this type of singularities. And what we found with a tight binding model from quasi-particle interference work is that we can have two different saddles. One is at a new point, this one. The other is created by this one, okay? With very tiny difference in the location of the two saddles. But this is the conclusion so far, because but it turns out that experimentally it's not clear what angle is precisely the octahedra rotated at. So we are more fine-tuning from the experimental results to see if it's possible to merge these two saddles to a higher order Van Hoff singularity, or this the final question, the final answer to the question. Moreover, using from quantum interference from the tight binding model with good, very good precision and good, satisfactory, we can reproduce for free the Fermi surface, which is close to the experimental one. So this is very, very close to getting the solution whether there is a higher order Van Hoff singularity here. Now, I was asked to mention possible other compounds that Van Hoff singularities exist. You can find basically everywhere now, because the experimental techniques are so much sophisticated, so much more sophisticated that they can detect this difference. One class is the Kagome superconductors, where they have reported several, very close to the Fermi surface, several different Van Hoff singularity. What means is that basically you have two parabolas that giving you conventional Van Hove singularity, but if they are a little bit more extended, it can easily go to a higher order Van Hove singularity and with more dramatic effects as we have discussed. And actually this twofold Van Hove singularity was associated with the charge order in the Kagome superconductor, this cesium, vanadium, antimony one. 3 minutes. The other one that, for example, closer, van der Waal material, indium selenide. And the reason I put this there is that you can tune it to a higher order Van Hove singularity, or almost flat, what they call flat band, but for us is a higher order Van Hove singularity, because you see how flat it shows here, and if you go to analyze, you question how flat is flat, basically, and you see that there is the possibility of higher order Van Hove singularity, but at high angles compared to twisted bilayer graphene. For example, that we need small angles and to create this. Another one is actually early enough band structure in atomic layers of hexagonal gallium chalcogenides. Okay? 3 different disulfur with 2 selenium or 2 tellurium. And there is a part in the, if you want to model the maximum of the ballast band, that scales as k to the power 6 cosine 6 phi. So there is potentially higher order Van Hove singularity there. But I would have missed something if I didn't. I want to refer to this paper, the catalog of flat band stoichiometric materials, a very recent one, Renaud and Bernevik and many co-authors reported they classified the flat band associate different materials with flat bands associated to localized Wannier functions, or to quantum interference effects, or to obscure Wannier functions. And they went down to a whole list of hundreds of materials. And the most important is to acknowledge my collaborators, Anirudh Chandrasekaran, my postdoc at Loughborough, and my longtime collaborator, Dima Efremov, are the main people that have done this work, and also my student Alkistis and group of Claudio Chamon, and the experimentalist group of Andy Mackenzie, and the groups at St. Andrews helped with the analysis. Thank you very much.
And I think maybe only one question, because time is very
Okay, so thank you for this presentation. So just for my understanding, so that I don't misunderstand something of your conclusions. So in your DFT calculations in all this bilayer ruthenate, right, you mimic the application of external magnetic field by introducing some magnetization per unit cell. Does it have some relation to the magnetization what is measured experimentally, so that there is some proportionality between you apply the field of, say, 5 Tesla and you get a magnetization of, say, 0.3 Bohr magneton per ruthenium, or is something artificial? And so, and the sub-question of this is that, so you observe a topological transition, right? At a certain magnetization value of 4.5 or something like this. Does it relate to the change of the propagation vector of the spin density wave, or is something different?
No, it's something different.
Okay, good.
It's something different. So one thing, I mean, the expert is who did the calculation is behind you. What we were trying to do is to get, because DFT calculations does not take everything into account, so it means that many things will get renormalized. Okay? But if you have sensible magnetization, that more or less will be associated with real, not exactly these values, but reasonable, let's say, values. And you see as a function of that Fermi surface, it conveys the message that, okay, take the real thing, modify your Hamiltonian and your the way you do the calculations, you should get exactly the same thing. So we wanted to get it qualitatively at that point, not relate exactly the numbers. That's the...
Okay. Good.
It's very close, but what you need experimentally is to tune the magnetic field.
I think we needed to stop because we not now have time. And thanks speaker again. Thank you.
So our session will start in 5 minutes.
Perfect. Mhm.
Good, thanks.
Should I share the screen already?
Yes.
Okay. Okay. Are you able to see it?
So, good morning. You are welcome on our second session. My name is Dmitry Efremov, and I will chair this session. So, we have 3 talks, and the first talk given online by Ilya Irion.
Okay. Can I just start?
Yeah, please.
Okay. Thank you very much for the introduction. I apologize. Unfortunately, I picked up a COVID last week and had to cancel my trip in the last moment, so which I regret very much. Anyway, let me give you, since I noticed that I'm a little bit off the topic of the session, let's see this talk as a kind of entertaining, giving you a status report where we are currently with respect to understanding how magnetic fermionic textures interact in proximity to a superconductor. Let me also mention that the work that I'm going to present has been done in collaboration with my PhD students, Amita here, and also with our senior colleague Anatoly Volkov, from whom we benefit a lot looking and learning about these hyperstructures. Although, of course, I'm not only going to talk about our work, but also give you a little bit of an overview on the subject. Now, you know very well, you have had, I think, at least one plenary talk on the subject, why you would be initially interested in looking into the proximity effect between a superconductor and the ferromagnet. And one of the major application currently in this field is the superconducting spintronics, which is basically based on the fact that you can have a long-range proximity effect between two superconductors, which is sandwiched with a ferromagnet. And the idea comes from the virtue that from the discoveries that has been done by Berger, Volkov, and Efetov, and also a number of other groups. There is a number of reviews on this, which I'm citing here. I'm also citing original papers on the next slide. But the idea is the following. So you have a superconductor, which is typically a spin singlet superconductor. So what is known is that if you have a ferromagnet and you have an inhomogeneous magnetization at the interface between the ferromagnet and the superconductor, what is actually happening is that the quantization axis is rotating. So which basically means that when spin singlet Cooper pair wave function, which penetrates into the ferromagnet, its quantization axis starts to rotate. And what actually is happening, so the first you do a spin mixing, and the second thing, because of the spin rotation out of the originally a spin triplet component, which is a total S equal to 0, you can create, by virtue of the quantization of the rotation of the quantization of the spin axis, you can create a component of the Cooper pair wave function, which is spin polarized. And the spin polarized component will be insensitive to the magnetization in your ferromagnet that can penetrate to a large distance. So this is something that has been theoretically predicted and also has been experimentally realized, and there is a number of groups which are working on this field. So this is, for example, one of the early experiments on this field, where you have two superconductor and you have a spiral ferromagnet with rotating magnetization and a ferromagnet by cobalt, where you can clearly see that without holmium, so without this rotation, without this spin spiral, your Josephson current is strongly suppressed. And if you have the spiral ferromagnet, then what is happening is that you have a long-range proximity effect, and your current voltage, so your Josephson current exists up to a much longer cobalt thickness, which of course also interesting because you can also try to polarize this current, and this is the reason why it's interesting for the superconducting spintronic. This is a field on its own, but now I'm going to ask a question: what happens if you take such a heterostructures and you consider a chiral magnet which hosts magnetic fermions? From the very beginning, again, it seems naturally that such a heterostructures with also rotating magnetization might be interesting from the perspective of the spintronics, but also there is another reason why recently people have been looking on this, I'm going to tell you in a little moment about this. So let me just, for those of you who are not working in the field of fermions, let me just remind you that this is the topological texture that can be characterized by a particular homotopy group, which is which is basically mapping the physical space spin orientation to the order parameter space. And in this case, for the fermions, you have spins with a fixed length on the two-dimensional plane, and your order parameter is a 3D magnetization. So what is actually happening is that your order parameter space becomes a surface of a sphere described by the two angles as 2. And you can have topological defects which you cannot easily remove in this case. And the most simplest examples of this are this simplest n equal to 1 topological texture, which are either Niel or Bloch fermions. And this is the example of the mapping to the order parameter space. And you can compute this winding number by simply looking on the changes of the magnetization. Again, originally this has been of interest in the field of high energy or particle physics, because Tony Stirmy proposed this object as a possible explanation for the formation of the elementary particles. But it actually very quickly also became interesting for the condensed matter system. So the first who've been looking on it were Belavin and Polyakov, who looked into the context of the nonlinear sigma model before Bogdanov and Jablonski in a ferromagnet, but actually the realization or the proposal to realize this magnetic skyrmions in the form of the skyrmionic lattices came by Bogdanov and Jablonski back in 1989, where they were playing around with energy magnetization, total magnetization energy of a ferromagnet, which can, with a strong Dzerzhinsky-Maury interaction, so which means with a strong spin-orbit coupling. And they have found that if you put the system in the external magnetic field, of course, you can also have other terms like crystalline anisotropy and so on. If you change the field, applied field, you start from a helical phase and you reach upon saturation fields, the ferromagnetic arrangement. But there is also another phase in between, which is a skyrmionic crystal, which is thermodynamically stable, in contrast to the single skyrmions, which are usually metastable objects. And they have been successfully realized by Mühlbauer et al. In 2008. Actually, for the sake of the story, one has to remind that this A phase has been indeed seen in MNSI. This is a system which indeed can be, let's say, to a first approximation described by this Hamiltonian. And the presence of the A phase was known for some time, but actually Mühlbauer was the first one who successfully shown that this phase is indeed corresponds to the skyrmionic crystal. And now, again, just for the sake of the further presentation, so these are our object, chiral skyrmions, Niel and Bloch skyrmions. And now let me also mention that these are the objects which are also familiar in the field of superconducting spintronics, because you can look on it as, if you make a cut along one of the radial direction, you will see that although the topology is lost, but you still have a very similar textures that as domain walls, Niel and the Bloch type of the domain walls. Okay, so now what is interesting is that this field is really booming in the book. So there is a number of, every year there are new materials which are discovered to find, to host skyrmions of the different types. And this is one of the most recent review by Takura and Kanazawa, where they see this objects. And what is also interesting that the temperature range where they see it is also very different. And what is interesting from the perspective of the superconductor is that they also see these skyrmions either as a metastable objects or like skyrmionic crystal, also at a very, very low temperatures. And which makes them an interesting object also to study in proximity to a superconductor. Now, let me come, apart from the superconducting spintronics, the reason why people started to look into this heterostructure is actually driven by the obsession of the field to find the Majorana bound states. Let me just remind you the original proposal that you have an S-wave superconductor, you have a semiconductor, you have a wire with a strong spin-orbit coupling like an indium antimonium, and you apply a field along the X direction. And in that case, what is, has been shown by virtue of the very simple calculation that indeed what is happening if you start with a simple two-dimensional electron gas, you split it by the virtue of the spin-orbit coupling, you apply the Zeeman field, and if you tune the parameter in the right regime, the Fermi level is crossing only one of the bands, and this band will be hosting spinless fermions. If now you put a S-wave superconductor in proximity to it, you will actually realize a topological superconductivity which should host Majorana skyrmions. So now let me tell you that here you have basically a magnetic exchange field, a spin-orbit coupling, and in principle, magnetic textures of skyrmions has both. It has an exchange field, and it's much larger than just an external magnetic field, and you have also an intrinsic spin-orbit coupling like a Dzerzhinsky-Maury interaction, which basically tells you that such a skyrmionic texture can be an interesting platform to realize topological superconductivity. And this was the reason why people also started to look into this. And you can nicely show that if you have this rotating magnetization, if you have a basically which you can describe by the local unitary transformation, you can basically show that by taking, if you assume that you have such a heterostructure we have now, a superconductor and a ferromagnet, and you have some two-dimensional electron guns which forms at the interface between those two, you can show that in this case, by the virtual proximity, you have superconductivity, and on this superconductor, you have an action of the effective spin-orbit coupling, which you can derive from the magnetization, and you can see that by doing this simple transformation, you can see that indeed having an Zaleshinsky-Marie interaction can be then mapped back, so to speak, into the effective Rashba type of spin-orbit coupling. And then if you tune again some parameters, the hope was that you can again realize Majorana bound state and topological superconductivity in the proximity between poles. Okay, so what is about the experimental and theoretical situation? So the theoretical problem that has been realized is that it actually turns out that for the simplest skyrmion that you see, namely Niel and block type of the skyrmions for the ±1 vorticity, it turns out that the Majorana bound states do not form. So you need to do something more. For example, if you go to the higher vorticity, so if you go to the even vorticity, you can indeed show that in such a case, you indeed can realize a Majorana bound state, but one of the immediate problems is that it's very hard to realize experimentally such a skyrmionic structure. Then there has been proposals that you can play with elongated skyrmions, although it's also controversial whether you can or you cannot see a Majorana bound state in this case. And finally, there has been recent proposals that if you look at the skyrmionic lattices, then if you, so such a skyrmionic lattice will be a whole platform for looking for such a Majorana bound state, and depending again on the number of parameters and depending on the position where you are located, you will be able to see, you should be able to see the Majorana fermions. But as you see already on the theory side, the situation regarding the finding Majorana appears to be quite complex. Regarding the experimental situation, it's also a little bit of a problem because you need to basically bring material which hosts skyrmions. This is, for example, one of the realizations that has been done by the Wiesendanger and collaborators, Kirsten von Bergmann, where they brought palladium iron iridate and were successfully showing that you do have formation of the skyrmions, which you can see, for example, here on the top of the rhenium 0001 surface. However, one of the problem always is that they had in this experiment is to prove unambiguously that there is an interaction of superconductivity with skyrmion. But this is one of the first attempts. Then there was another experimental realization where people wrote a cobalt monolayer also on the ruthenium. Here it's on the rhenium, here it's on the ruthenium layer. That's all type 1 superconductors. And actually it turns out that indeed, again, they were able to show that in such heterostructures, they do see a formation of the skyrmionic objects. But again, what was essentially still missing is to show that there is an interaction between a superconducting substrate with corresponding skyrmion. So, and then there was another proposal from France where they looked into the molybdenum silicate on platinum, cobalt, ruthenium, where they saw some signatures also of the interaction between skyrmions, or probably some effect of the stray fields, which they saw in the flux spinning in a superconductors, where they could clearly see that there is some interaction between the two, basically two parts of the interfaces. However, still the problem was that they could not unambiguously show that they could see skyrmionic stabilities. So this brings me to another question. So if it turns out that looking into the skyrmionic superconducting heterostructures is maybe not beneficial at the first glance to realize Majorana fermions, you can ask another question. And the question that we were also looking at is, in principle, you can also ask whether this type of topological defects can interact. So we know that in a superconductor, you have a precursor vortices. In a chiral magnet, you have block or near fermions. These are topological defects. And the natural question arises, how do they interact with each other? And the original proposal was made by Mark Radner and Christian Heiss and collaborators, where they actually proposed that such an interaction may occur if there is so-called superconducting magnetoelectric effect. So which basically requires that if you have your skyrmions, it basically the polarization of the skyrmion generates some supercurrents, and such are supercurrents by the virtue of the spin-orbit coupling start to interact with superconducting vortex. They basically propose that if the spin-orbit coupling is relatively large, then the supercurrent indeed, which is basically created by the skyrmionic stray fields, should generate vortices. Now, we looked on this problem on a simpler basis by essentially suggesting, well, maybe we can consider on the problem on the different side. So let's assume that there is no proximity in a certain sense. Let's assume that there is no direct interaction between your chiral magnet and the superconductor. So we even assume that you can put an insulator which prevents to have direct exchange interaction. And this is something that typically you don't even need to create. It's something which is created automatically when you create such a data structure. And the only way they interact is that, of course, we know that in a type 2 superconductors, you apply an external field, you will generate vortices, and these vortices will have also large stray fields, and this stray field of the vortex can actually interact with a skyrmion. So there is no direct proximity effect. The only interaction is virtue of the electromagnetic field, but the electromagnetic coupling. Okay, so then you take basically, in order to strengthen the effect, you take a thin film, and we know that in the thin film, when the penetration length is much larger than the thickness of a superconductor, you have pure vortices. And good advantage of these pure vortices is that they are weakly screened, so their stray field is going well beyond the superconducting film. And it has also a characteristic length, lambda, which is lambda squared over dsc, which is giving you the size of the pearl length, which can change up to 1 millimeter. And this is something that you can also change experimentally. And also you have a long range vortex field. Okay, so then the idea that you are going to do is exactly the same that Bogdanov and Yablonsky has considered, except that now you add an extra term. So imagine you have a chiral magnet which do not have a direct interaction with a superconductor, and the only interaction you have, because you have by the application of the external field, you also create vortices. And this vortices has a profile, and of course the profile of this vortex field will start to interact with a profile of your skyrmion magnetization. So essentially, by assuming, or by basically solving, assuming that you're in the regime where there are individual skyrmions or skyrmion lattices, and you have a vortex lattice, you start to interact by the virtue of this interaction. Okay, and then if you do so, then this is how the interaction energy can be described in this case. So this is your usual terms you have in a chiral magnet plus the stray field from the pearl vortex. And of course, it's not a surprise that depending on the polarity of the vortex, you do generate attractive interaction, depending on whether, and you see that this is the case actually, independent whether the typical size of the vortex is much bigger than the skyrmion radius or other way around. In both cases, you can generate attractive forces for a certain polarity and repulsive forces. Now, in order to see whether the whole configuration is thermodynamically stable, so you now try to minimize total energy, assuming that you have a skyrmionic and vortice lattices, and you look the condition for the total minimum of the energy, and there you can actually see is that if you do so, that the configuration is actually stable, despite the fact that initially we saw that the attractive forces are generated for both cases. But if you start to look into the thermodynamic stability, you see that it's actually only stable if you are dealing with a large skyrmion radius. So the skyrmion is larger than the typical length of the vortex. This is all very nice. So that's basically if you now summarize what you want to have, so for the exchange coupling, so that's the one which was proposed by Radner and collaborators, that they argued that you can have skyrmion-induced current must spatially coincide with the vortex current to reduce the total free energy of the superconductor, and they put a condition when it can happen. Whereas for the stray field, we also formulated the condition under which the skyrmion's vortex pairs will be stable. Okay, so now let me mention that such a proposal that has been made has been recently realized. Let me just spend 1 or 2 slides on this. So again, the problem is in this community is that you need to have 2 types of, so you need to have experimental groups which are experts in both, basically in the skyrmions, because you need to find an optimal balance to modulate the skyrmion radius and the skyrmion stray field amplitude. And at the same time, it has to be someone who is also is familiar with the field of superconductors, because you need to also optimize your superconducting field. And so this both combined in the group of Christoph Panagopoulos in Singapore, where they made some engineering in order to find an ideal match of, let's say, elements containing so iron, cobalt, platinum, and iridium in order to model the strengths of the Jalasinski-Marie interaction to optimize the size of the skyrmions. And this is what they did here. For these heterostructures of the 47 nanometers, and at the same time, they also found the superconductor niobium platinum, and which they also put with a certain. So this is niobium 25, and they put some coverage with platinum in order to effectively fix or modify coherence, superconducting coherence length, and that's of course done in order to modify the size of the vortices. And this is also what they have shown here that they were able to do. And now they match both. And actually they were looking, and the paper has been published last year. What is interesting is that they try to see essentially 2 effects. So they try to see the effect that we have predicted, where you have an insulator, where you try to avoid the Edelstein effect, and the only way the 2 heterostructures are interacting with each other are only by the virtue of the stray fields. Or you can also have a direct contact. Of course, stray fields will be interacting also, but in addition, you also expect to see maybe effects related to the stray fields, to the Edelstein effect. And if you now compare the numbers that you get, that they measured in all of this substrate, you see that you have exactly the conditions that we have been proposing, whereas skyrmionic radius is larger than the corresponding coherence lengths, the corresponding size of the vortex, and all of them are much smaller than the lambda. Okay. So first, they indeed have been able to successfully show that indeed there is an interaction. This is a measurement of the bulk magnetization, and you clearly see that in contrast to the typical behavior of a superconductor, you see indeed a transition that is basically connected to the formation of the skyrmion nucleation field that they see here, and they see that the effect is changing in this going from the heterostructure with the insulator in between to the and the superconductor. So which basically clearly argues that they indeed see the formation of both vortices and skyrmions, and they see a strong anti-vortex response in MS films because they see a larger drop in this case. And this is all a very good indicative factors that they do see that there are both skyrmions and the vortices, and they do interact with each other. Then they also see that the skyrmion induced, so the skyrmion should also, the stray field of the skyrmion should induce the critical current. This is also that have been discussed by us. And they also clearly see this in the range where the skyrmions appear. So they basically do see that the topological structure pin fluxons. And this is the first step why where they see that two types of textures start to interact with each other. Of course, that's still a thermodynamic probes, and they haven't managed yet to show spectroscopically or by help of, for example, raw and stems that they see both skyrmions and underneath of the vortices, but this is something that I believe can be done. Now, let me come back to another proposal, to the proposal that I was saying is unsuccessful, namely the prediction that you can have maybe Majorana fermions underneath of a skyrmion in a superconductor. And I told you that the problem was that it appeared that for excuse me, for the odd number of for the odd vorticity of the skyrmion, this is not possible. It actually turns out, and this has been a proposal by the Karlsruhe group, that now if you have combined composite objects where you can combine a vorticity of the skyrmion and the vortex, it actually allows you to generate Majorana state, which is emerging at the skyrmion core. So which is again coming back to the question that such a composite texture, skyrmion vortex, might be now again interesting to look from the perspective of realizing Majorana fermions. Now, there has been another interesting proposal, basically about why to have such a pair would be advantageous. And the reason is that if you have, so one of the problem, for example, to have skyrmions, magnetic skyrmions for the application in various memory devices is that surprisingly is that skyrmion is a topological object. And the reason is that if you apply a current along x direction, there is a transverse movement, which is exactly connected to the skyrmion Hall effect. Therefore, skyrmion is really relatively difficult to manipulate in contrast to the domain wall, for example. Now, if you have a composite pair, that becomes also another interesting way of manipulating such a pair, because you can, of course, move the vortices and the skyrmion. There has been a proposal by Milosevic and others. And of course, another proposal has been just published is that once you have this, so there has been a proposal, how can you scale such an object having Majorana fermions? Again, here theory is well ahead of the experimental realization, right? Okay, now nevertheless, let me now spend the last 2 minutes on the other interesting points from where I began my talk. Remember, I mentioned that the initial interest in looking on the inhomogeneous magnetization in a superconductor in a magnet is that you can arrange to have a long-range proximity. So now coming back to the true proximity effect, so one of the interesting proposal would be that once you have a skyrmion, which is at the interface with a superconductor, of course, it will also create, you can understand in the following ways, that it will create the Cooper pairs, and the Cooper pairs on the superconducting side will try to reflect, of course, the profile of the skyrmion, which will be on the ferromagnetic side. And that is interesting because it's in principle gives you a very sensitive way of looking on this interesting magnetic texture with a Fraunhofer pattern. And there should be a distinct pattern for magnetic skyrmion. That's one proposal. The other proposal is that, of course, if you have such a, skirmions, and here it is such that I already mentioned that in many respects, the behavior of the skirmions is very similar to the domain wall. So you can, for example, view a skirmion as something which is two domain walls, which is elongated along this direction. You can see how the long-range triplet component is modified, and this is something that we have looked that the paper has been published this year. Depending on the various type of the filtering, you can get additional contribution, which you can either enhance various components or suppress, depending on whether you are looking on the charge current or on the spin current. Okay, I think my time is up, and let me now summarize. So I try to give you a kind of an overview where we are in looking at interfaces hosting skirmions and a superconductor. So first of all, there is a very interesting experimental realization of the composite pairs, the vortex skirmions, which is interesting from the perspective of finding topological superconductivity and Majorana bound states. There is still something which is not fully explored, namely how the Josephson current is modified in presence of the skirmions. But what we saw is that this Josephson current, if you are looking onto the skirmions between two superconductors, you see that you can use the Josephson current because you can force torque on the skirmion, forcing it to move, which is another way of manipulating skirmion. And of course, another proposal is the inverse proximity effect, where the skirmion should have given a special pattern for the Fraunhofer pattern. Okay, let me stop at this point, and thank you very much for your attention. Okay, Dima, I don't hear you if you're saying something. No, still don't hear you.
Okay.
Oh, now I hear you. Okay, great. And now again, not.
Okay. Do you hear?
Yes, now I hear. Yes.
Okay. Great questions. Okay. Let me then ask a question. So basically, now what you are told is this is basically technology of the some films on top of other films, skirmions. What is the perspective for having monolayers superconducting and monolayers magnetic?
You mean now the question is whether you can have bulk material where you have both vortices and the skirmions, or a skirmion
Okay,
type of
this is the
check?
first question.
Or you?
Both.
Oh, you mean to have material where you can do MBE in order to have a layer which is skirmion and another one which is superconducting one? Well, this is a field of 2D materials. I know that there are realization. Actually, I think they are from Theo Dresden, if I remember correctly, by one of your colleagues, experimental colleagues, which have shown that you can have realization of the skirmions in some of the 2D magnets. I don't remember exactly as the chemical composition. There is always a problem, as you know, that putting the system in contact to each other is that superconductivity is easily suppressed. Is easily suppressed by putting, proximatized to a magnet, and that's one of the reasons why you would like actually to avoid the strong proximity. So far, I'm not aware of the realization in the field of 2D materials. Concerning bulk materials, there has been proposal, as you know, in some of the iron-based superconductors. There is a claim that you can have a magnetic phase, which is spin vortex, And such a spin vortex phase coexist with superconductivity. But there has been, I think, a work also from Copenhagen, from Brian Anderson group, where they try to see whether you can have some topological superconductivity occurring in this case. But again, it's pure theory consideration until now. Experimentally, I'm not aware of.
Okay, one more question, if any. Okay, we are behind the schedule. Let us thank the speaker again. And the next talk is, yeah.
Thanks very much. Yeah.
The next talk is from Igor Morozov, who is presenting us the perspective of synthesis different van der Waals materials.
Presenter this. Okay. Like that. Okay. I may use this, but not this. Yes. Okay. Okay. Microphone. Okay. Dear colleagues, first of all, I want to express my gratitude for all organizers this beautiful conference and the possibility for me to present this report. Some part of these results, important part of these results was prepared in the work of my diploma student Anna Vorobyova and PhD student Andrei Shilov, and some details of this work we may see in the tomorrow in the poster section. These posters, you can see number of these posters. Discovery of iron band superconductors was the one of the important in the physical and chemical scientific world in 21st century. In this slide, we can see some examples of this family of some iron-based superconductors, and we can see that the simplest this 1,1 family. This is the van der Waals compound, because we can see not charged layers, and we may split this very not without problem. And we can see that oxygen-free iron-based superconductors have some preliminary, because we may prepare this compound in the form of big single crystals that very important for physical measurement. This compound, this is the 111, 111, and 122 family. This compound consists of the negative layers, anti-fluoride layers with composition iron arsenide, and cation of alkali metal in the case of 111, or alkali earth metal in the case of 122. Between this layer, we can see these metals, these cations. And this is important, for example, when we prepare samples for ARPIS after cleaving, some one half atom of lithium stay in this layer and one half go out. And this is very important because this is like van der Waals compound. We prepare neutral layer, and this is very important for measurements by ARPIS, for example, because in the case of 122 family, alkali earth metal stay exactly in the center of between layers, and after cleaving, the layer have some charge, and this is not suitable for some measurements. The layer is the square lattice with iron atoms, and the atoms of arsenicum up and under the square in this letter. As a result, all iron metal have a tetrahedral coordination of arsenicum atom. The layers nature of this compound we can see in this photo. This compound was prepared with some substitution for investigation nematic properties of this compound. And some compound was prepared the first time, and when we put when substitution level increased, the temperature of superconductivity increased, like we know for lithium iron arsenide. And then we decided to investigate what happened if we change arsenicum and phosphorus to more heavy pnictide for bismuth, for example. And checking in crystal structure database, we can see that only some amount of the metal may to organize the same structure like 111. This is the manganese. All compounds with all pnictides and all pnictides and all alkali metal from lithium to cesium crystallize in the same crystal structure of lithium iron arsen. I think this stability because manganese have big magnetic moment, and interaction between magnetic moments of manganese stabilize this structure. Another the metal which may stabilize this structure, this is zinc and cadmium. We can see that this compound demonstrate different structure type, and we can see that crystallization, some of this structure, this is the function only the ratio between radius of alkali metal and radius of the metal, and nature of pnictides not important for this. For example, we can see that if this ratio very big, for example, we can take rubidium and zinc. Rubidium more than two times bigger than zinc, and in this case realize this structure type. And and this structure type exactly like lithium iron arsen. But we can see that structures with bismuth is absent. only very little amount of compounds with bismuth was structure was known when we start this work. In this slide we can see experimental condition for preparation 111 single crystals. We used cell flux method. This is the start composition for crystal growth. We put our precursors to aluminum crucible, seal this crucible to niobium container, and then sealed this container to silica ampoule. As a result, we prepare some bismuth compound. In this picture, we can see sodium cadmium bismuth. This crystallizes in orthorhombic space group. In this structure, we can see like graphite layers, but these layers exist some connection between these layers and sodium between this hole in this structure. Band structure calculation show us some interesting details and the physical properties of this compound under investigation. When we change cadmium to zinc and the ratio is more decreasing this ratio, we prepare a compound with structure of lithium-ion arsenic. After 1 year after we publicate this data, structure data, some theoretic calculation of band structure of sodium zinc bismuth was publicated, and in this work we can see that this compound may be a very interesting variant with dual topological insulator phase in this case. Some interesting variant if we change some bismuth to antimony atoms in this structure, because by theoretical prediction in this solid solution some interesting composition exists with some direct points, and in our work we may prepare some these compounds. This is interesting that for preparation this compound we needed to use start mixture with very amount quantity of bismuth. For example, if we take 95% of bismuth, we prepare crystals in which only about 1% of bismuth exists. And when we use alkali metal and the metal with big ratio of size of alkali metal to the metal, we prepare compound in the space group P63MMC. This is very interesting structure because atoms of zinc and bismuth organize ideal hexagonal layers, and alkali metal stay between these layers, and distances between layers very big, and this compound, like van der Waals compound, very easy exfoliate. band structure calculation for rubidium zinc bismuth show that band structure, this compound, very close to band structure potassium zinc bismuth. This compound was synthesized about 2 years earlier, and in this compound exists surface superconductivity, and some Dirac point exists in this structure. As a result, we prepare some new bismuth-containing compounds, and for suitable presentation, we may use this table. We can see that, for example, if we take potassium and zinc, we may prepare four different pnictides from phosphorus to bismuth with the same composition, with the same structure. And if we compare the physical properties of this compound, we can see that from phosphorus to bismuth, phosphorus, this is isolator, and band gap decrease when we change phosphorus to arsenicum, to stibbium. In the stibbium, for example, calculation take about band gap about 0.03 electron volt, and for bismuth we have the properties of topological properties we may have in this case. If we check another compounds with pnictides with composition 111, we can see another two families, and we can see that very often realized this is interesting group with like graphite layers, and we can see that some places now is empty, and this is very interesting for future work. And then we try to prepare compounds with bismuth with analogous structure like 122. It's interesting that only one compound was before our work. This is the barium manganese 2 bismuth 2. And we use the cell flux method, and we prepare 4 compounds with the composition 122 and the structure of iron-based superconductor. We can see in the photo that this is the very soft, like foil crystals, and these crystals very easy to exfoliate, like van der Waals compound. And this was very big problem for crystal structure determination, because this is not possible to take these crystals without destroy the because layers change, move, and this is not a single crystal now if we take this small piece. But in the case of rubidium cadmium 2 bismuth 2, after very much amount of experiments, one crystal was okay, and then we may use like model these results, and structure was determined by X-ray powder diffraction data. In this picture we can see a structure of this compound, we can see antifluoride-like layers, like in 111 and 122, and all iron-based superconductor. This is the very important layer responsible for superconductivity. And we can see alkali metal between this layer. This is the polyeders of iron, of rubidium and bismuth. And this is very interesting that distance between the layers may change very strong if we change small zinc to big cadmium. The reason of this very big change in the distances, this is the mechanical reason, maybe I may say this, because in polyeder with rubidium, distances in the main diagonal, the same in this case and this case. Main diagonal stable, but distances between atoms of bismuth, in this case, smaller one, because this is the part of tetrahedra with zinc. In this case, distances between square in the bottom, this is the part of tetrahedra with cadmium, and this distance is more bigger, and we can see that this polyeder is the highest is compressed, and we can see that this distance, for if we used effective unique radius of bismuth 3 minus 3, this radius about 2 angstrom, and we can see that these distances, we make conclusion that exists some interaction between atoms of bismuth in this case. I think this is very important because the preliminary results of ARPIS measurement show us the very interesting shadow bands like cuprates, and calculation, band structure calculation, the same result, very picture very close to the picture for classical cuprate superconductors. And in magnetic susceptibility, we can see some interesting change in the low temperature. And this is very interesting because this family of bismuthides with structure of 1 to 2 have some interesting properties. This is not simple role implemented. If we calculate valent electrons to formula unit, you can see that this is only 15 electrons, but for simple rule, we needed to 16 electrons, 8 electrons for bismuth atom, and does mean that this is the very interesting problem for this compound, electron deficit compound, because if we take analog with iron, for example, rubidium iron 2, arsenicum 2, this is not problem because iron may have valence 2 and valence 3. This is not problem with this deficit of electrons. But in this case, we have zinc and cadmium. These atoms have stable valence plus 2, not another. And maybe this result because maybe some charge density waves in this compound realize. And for finish of my work, I I want to show some interesting result with another compound. This is barium aurum 2 with Mu2. In this compound exists some deficient of aurum atoms. If we see ideal structure of this compound, this is very interesting. Exists inversion. This is the classical antifluoride like iron-based superconductor layers, but in this compound exist layers in which bismuth atom stay in the layer and aurum atom stay under and under and down of these layers, and exist connection between these layers. And this compound show superconductivity. This is very interesting because you know that for aurum superconductivity is very random property. Yes, I finish my talk. This is my colleagues who took part in this work. And thank you for your attention.
Okay, thank you. Questions?
Thanks for the nice talk. I have a question for sodium and zinc bismuth and alloyed with antimony. You put the antimony into the bismuth side, right? And I saw the lattice parameters. Does that go to linear, or is that changes like step like change? Do you have the data for? I saw the data, but can you show me?
Could you repeat the question because
So the lattice parameter goes to linear change or not?
linear change
With antimony, bismuth antimony. Probably just first half, but.
You ask about this?
Yeah, that
Yes.
one you changed bismuth side with antimony, right? Antimony.
Okay.
Yeah, this one.
This is very big difference between composition of initial
Okay.
initial compositions and the composition of crystals. We can see that antimony go to the crystal. All antimony from melt go to the crystals. This problem, but we may prepare crystals if we take very much amount of bismuth and small amount of antimony.
Okay. Yeah, thanks.
so, questions? Other questions?
So maybe I have a more general question. So we present very beautiful work on synthesis of these difficult to synthesize crystals, right? So that was really a great effort invested in that. So what are your expectations from the side of experimental physicists? What kind of highlights do you expect from different kind of measurements? Like, for instance, you mentioned already, so the band structure, so the ARPES data, which shows some shadow bands, or in the other materials, so there are superconductivity. What else? What is the driving force? What could be the driving force and the leading idea for the experiments?
Now we needed to measure physical properties of this compound, and firstly we plan to measure transport property in the field, and maybe Hall effect for check some topological properties, and very interesting to check by ARPES this compound. Now we this is in progress, this investigation.
Okay, I do not see any more questions. Yeah, thanks. And the next, yeah, and again, this certificate for you. So, the next talk is again online. Is given by Kataev. Oh. Katanin and okay, and the title talk you can see here. Do you hear us? No? Hello?
Yeah, hello.
Yeah, Andrei.
Okay.
Yeah,
Yes. Do you see my slides?
yeah, we see you.
Okay. The title of the talk is Charge and Spin Correlations in Graphene and Graphene-Based Materials. I am Andrei Katanin from Moscow Institute of Physics and Technology. The first part of the talk will be about the clean graphene, which is a well-known material. It consists of one layer of carbon atoms, which are arranged in hexagonal lattice, and it's well known that the electrons in this material possess massless direct dispersion. And the peculiarity of this dispersion is that the Coulomb interaction is not screened. Namely, the polarization operator remains proportional to momentum, and therefore the renormalized Coulomb interaction is different from the bare one only by a factor. And this yields many kinds of peculiarities of electronic and other properties of graphene, which I will discuss. The first suggestion came even before the graphene was synthesized experimentally, is that for sufficiently strong Coulomb interaction, the excitonic or charge density wave instability occurs with the order parameter, which is given by occupation of electrons of two different sublattices. And after the graphene was synthesized, this activity was continued, and some results on the critical Coulomb interaction were obtained for this charge density wave instability. And this table summarizes some of them. So the first four rows are for the mean field studies of different kinds, and the last row is Monte Carlo study. And one can see that as concerns for the mean field approach, one can get very different results for the critical interaction, starting from, say, 0.8 to even infinity. But one particular kind of mean field approach, this dynamic polarization operator, but the Fermi velocity yields more or less agreement with Monte Carlo analysis. And why the Fermi velocity should not be renormalized was considered in this paper. I will not address this point in detail. This is related to compensation between renormalization of Fermi velocity and vertex corrections. Another kind of Monte Carlo analysis was performed later for the spin density wave instability, starting from these papers. They show that there is some critical Coulomb interaction for spin density wave instability, and most comprehensive analysis was done in this paper in the coordinates of short range part of the interaction and long range part of the interaction. And one sees that there is a region of spin density wave instability, which is marked by blue line here. But the actual graphene freely suspended graphene is in this shadowed region, which was not investigated by this Monte Carlo analysis because of the sign problem. And also the charge density wave instability was not found there by the same reason. Therefore, we see that quantum Monte Carlo analysis doesn't provide full information on various instabilities, and the question here is whether one can develop diagrammatic approaches. Is graphene in the proximity of charge instability? Because if you look at this value, it's much smaller than the actual interaction in graphene. In graphene, the parameter alpha is 2, so it's twice bigger than the critical interaction found in Monte Carlo. And another question is, if those instabilities are not present, how strong are charge and spin correlations in graphene? We started with functional renormalization group analysis of finite graphene nanoplates with zigzag edges, like shown here to the right. And we use the so-called coupled ladder approximation, which was first suggested in this paper to parameterize the dependence of interaction vertices on position of electrons. For the interaction, we use two kinds of interactions. One can be considered is the ab initio realistic interaction calculated first in this paper, which is shown schematically here. The case is 1 over R, as it should be for the unscreened interaction. And for comparison, we consider the uniformly screened interaction of this kind, which contains a bare Coulomb interaction and the 1 over R decay at larger distances. The difference between the two interactions is at the smallest radius of the interaction, and it occurs because of the screening of interaction by sigma bands of graphene in the realistic calculation. And here is the resulting phase diagram. To the left, we see the phase diagram for realistic interaction. One sees that there is a region of charge density wave instability, which was hidden in the QMC analysis I presented, and the spin density wave instability. The freely suspended graphene is marked by plus symbol here. It is far enough from both charge and spin density wave instabilities. But if we calculate the susceptibility with respect to the spin density wave order, it's substantial. So the spin correlations appears to be enhanced in freely suspended graphene. For comparison, on the right hand side, I present the results for uniformly screened interaction. One sees that spin density wave instability remains more or less at the same place as it was for realistic interaction, but the charge density wave instability drops substantially. So this was the result for the ab initio interaction. This is the result of charge density wave instability for the uniformly screened interaction. And if the interaction was just uniformly screened, graphene would be on the verge of the charge density wave instability, which is not the case because of this additional screening by sigma bands, which I mentioned here. To go further, we should emphasize that this functional renormalization group approach is actually oriented towards weak coupling. It's okay for graphene. One sees here that the results for spin density wave instability agree well with QMC analysis. And also the charge density wave instability, we get here the correct we get here the correct alpha of order of 1, as it should be from point of view of Monte Carlo analysis. But if we want to study some other materials which are strongly correlated, we should find a tool which is capable to treat the strong Coulomb interaction, metal insulated transition, etc. For that, we look deeper what is hidden in this coupled ladder approximation, which I mentioned, and it decomposes the renormalization of the vertices in 3 channels. The transverse channel is taken fully local. and the longitudinal channel of this kind is taken non-local. And this brings the idea to start from the purely local limit and then include some non-local corrections on top of that. And the local limit is the DMFT theory, which we apply here in taking two lattice sites and taking local bath, some bath green function, which is obtained self-consistently, and the interaction inside of these sites and the inter-site interaction. So this forms the local problem we study. And then for the non-local extension, we just consider the ladder of the ladder diagram with some local particle Hall reducible vertices which are extracted from DMFT. And this yields the non-local correction for the susceptibilities. So for the phase diagram, we obtain something very similar to the functional renormalization group approach. You can see that the charge density wave instability almost lies on the top of the functional renormalization group approach. Spin density wave instability is a little bit shifted, but qualitatively reproduces the correct result, which means that this method indeed works and describes correctly the possible instabilities. One can plot now, since this is all performed in symmetric phase, one can plot now the spin and charge correlation functions, and one sees that indeed the spin density wave instability, spin density wave susceptibility strongly enhanced around the momentum, which is here marked as 0, but this corresponds to staggered component of the susceptibility. So this one is enhanced, and charge density wave fluctuations are not as strong. Now we can apply this tool for really strongly correlated material, which is the twisted bilayer graphene. These are two sheets of graphene rotated by a small angle with respect one to another, and this is produces well-known narrow bands and mode insulating state at some fillings and superconductivity near these fillings. So we take the ab initio dispersion which was obtained in this paper, it's shown here to the left, and we take the ab initio column interaction, which for small rotation angle is shown here by black line, and it can be parameterized by this dependence of the distance on the distance. Now we take additional piece of the interaction, which is the intra-valley magnetic exchange. It was discussed in these papers. We take the most important component, which is the nearest neighbor intra-valley magnetic exchange. And due to restriction, because of restrictions of the impurity solver we use, we take only Ising part of that interaction. These are the the resulting spectral functions we obtain. For the even fillings, they form a mode insulating state with a pronounced gap at the Fermi level, here for n equal to 2 filling of the Maria-Brilliant zone, and here n equal 4. And for the other fillings, they correspond to the metallic states of the electrons. This agrees with the experimental observation that the resistivity increases at the even integer fillings, like we obtain for the spectral functions, and form of the spectral functions even qualitatively agree with some STM spectra, which were taken on small angle twisted bilayer graphene. We also calculate, by the way, the interesting point of these spectral functions is that these peaks of the spectral functions are often associated with Van Hove singularity. This is absolutely not the case, because if you look at the distance between these peaks, this is 20 MeV, while the dispersion was, the bandwidth was several MeV. And therefore, these peaks are just broadened at local levels and have, in fact, nothing to do with Van Hove singularities. We also calculate the local charge and spin spectral susceptibilities. One sees these narrow peaks of the order of 10 to the minus 2 MeV on the scale of 10 to the minus 2 MeV, which show that the charge and spin degrees of freedom are strongly localized at integer fillings, which are considered here. And finally, we consider the non-local charge and spin susceptibility. We find that charge susceptibility is odd in Valley and even in sublattice index, and spin susceptibility is even in the sublattice index. Say for the filling of 2 electrons per Maria unit cell, this corresponds to such a filling that they prefer the same Valley, since the charge susceptibility was odd in Valley index, and prefer different sublattices AB or spots of the lattice AB and BA. And this is one of the states, SU4 states, which was discussed in the strong coupling approaches of these papers. So here we confirm the existence of such state starting from basically tight binding model with sufficiently strong Coulomb interaction. And for the non-local susceptibility, which is shown here, it looks more or less the same for both charge and spin. We obtain incommensurate pattern of the non-local susceptibility, which shows that this state changes from one part of the lattice to another by flipping spins and moving electrons from one valley to another on some short range distance. So here is the conclusion of my talk. We find the charge density wave instability in graphene at sufficiently small, unphysically basically small permittivity epsilon. The boundary of charge and spin, the boundary of charge instability is strongly shifted by realistic screening of Coulomb interaction. The spin density wave instability occurs also at unphysically large local interaction. Therefore, freely suspended graphene is in the semi-metal phase, but possesses strong spin correlations. And in twisted bilayer graphene, we find a kind of SU4 state, odd in Valley and even in sublattice index, with incommensurate charge and spin correlations. The perspectives of the methods are the following. One can study dynamic excitations, looking not only at static but also at dynamic quantities, study superconductivity, and apply to the other materials of interest. Thank you for attention.
Okay, thank you. Questions? So, let me ask the following question. What kind of experiment we should do just to see for this is, first of all, charge density wave state, and concerning layer graphene SU4 state?
So one probably should look at the distribution of charge at the graphene plate. And therefore, this could show the possibility of charge density wave. Yeah.
And SU4 state?
For the SU4, it's a little bit more difficult because one cannot easily resolve this kind of combinations of valley and spots. All of them are combined, of course, in the real experimental picture. And here I'm not sure what kind of experiment should be performed to see presence of this state. What is most important is this maybe ferromagnetic alignment of spins, local ferromagnetic alignment, which can be probed, I think, somehow in experiment.
Okay, thank you, and
Thank
let
you.
us thank all the speakers of this session.